Been invited by the SEG Women's Network to give this webinar. Now, due to unforeseen circumstances, the host of this meeting is not able to host the meeting, so she has found two other people hosting the meeting. One of them whose microphone doesn't work, so she apologizes for this. But I've been encouraged to simply go ahead and introduce myself and start the webinar. I'm very pleased to see a reasonable number of attendees. Very happy to see some familiar names also in the attendees. Some of you may know me. But just to briefly describe who I am, my name is Femke Vossepoel. I started my career in aerospace engineering, where I did a PhD on the use of satellite radar observations for ocean circulation. I spent a number of years in oceanography research and then moved discipline to work at Shell in a research and development department, still using similar techniques that I used in oceanography and combining numerical models with data. In oceanography, it's called data assimilation. In reservoir engineering, it's better known as history matching. And within my time with Shell, I moved from a more reservoir engineer position as a scientist to a geophysicist position. So I've seen both worlds. After my time with Shell in 2007, I started my time with Shell in 2007, and in 2016, I joined TU Delft, the university where I obtained my degree, as an associate professor, and I'm still in that position. I'm very pleased that today I can share with you the application of data assimilation, so a technique from the geosciences, for the forecasting and the assessment of the current COVID-19 pandemic. And with that, I'd like to start my presentation. I'm happy to take your questions during the meeting, but I may not always see the chat screen, so it may actually be better to wait with your questions until the end, so I can take them then. The agenda for today is as follows. First, I'll start with an introduction. What is data assimilation? As I mentioned before, it's a technique that originates in meteorology and oceanography and has been applied in many other disciplines. I'll describe to you how it has been applied in reservoir monitoring, in reservoir engineering as assisted history matching, and I'll mention a number of data assimilation methods. I'll then go on to the core piece of this presentation on the use of this data assimilation technique to study COVID-19. And I have some slides on ongoing data assimilation research in our group, but I may not have time to go through that. I'll end with a conclusion. But first, what is data assimilation? The best way to explain it is to talk about how weather predictions are being made. And that's illustrated here in this graph, where we start at some initial conditions and we want to forecast, let's say, the weather, the temperature for our next day. So we run a model, and then as soon as observations come in, we may discover that our model prediction is actually not that's correct. So we use that observation and we use the knowledge that we have on the errors in the model and the errors in that observation to find the most likely state given the observations. So suppose this was temperature, we were estimating the temperature too high, the observation tells us it's lower, and we correct the model. Typically in oceanography and meteorology, we correct the state, so that's the temperature, the pressure, velocity. But in solid Earth applications, we may correct the parameters of the model and thereby come to a different model trajectory. I'll come back to that later on in the presentation. Starting from that new corrected model state, which we call the analysis. We run another forecast until the next meeting measurements come in, and then we do that again and again, and that's how we obtain the most likely trajectory. Now you see that this is an example of sequential data assimilation where we sequentially update the models, but we also have something like a smoother that takes into account all observations at once, and then creates a more smooth trajectory. And we have methods that change the initial conditions and then use variations on those initial conditions, and they are known as 3D VAR and 4D VAR methods. In solid earth geosciences, and particularly in reservoir engineering, data simulation is used in the concept of closed loop reservoir management. And that closed loop reservoir management concept is illustrated here by a cartoon of my colleague Jan Dirk Jansen, where he explains how the optimization of your production strategy can be done with the models that have been optimized or that have been improved with the help of data. And the improvement of those models, typically we have multiple models to represent the full range of possible models. The update of that model is done with data simulation algorithms. So considering your reservoir and your contour of your reservoir in terms of rates and pressures as one system, you could think of the input into your system where you say, okay, I want this pressure, I want this rate, and this is how I configure my wells, and you get the output, which is then measured, and you use that output, so typically the production rate and the pressures, the bottom hole pressures, to update what you know of the subsurface, and that is based on the geology, the seismic, the well logs, etc., the dynamic reservoir model, the flow model, and you use then the best possible reservoir model to optimize your control strategy. So there are two loops in this closed loop reservoir management, and it's the red loop that uses data assimilation algorithms. And these data assimilation algorithms are the same algorithms as that I explained in the previous slide that have been used for decades in oceanography and meteorology. Now, the main ingredients of data assimilation, as you may have guessed from my introduction, are a model and observations. And we typically, there are different notations, and I may not always be consistent in this presentation, but typically we denote the state with the letter X, and we have a subscript that indicates where we are in the time. And we, based on a certain condition now, based on a condition yesterday or a previous time step, we run a model so we can predict what will be the state today. But we realize that at least in meteorological and oceanographic systems, we have noise in the system, and hence we introduce this beta, which stands for a chaotic or noisy forcing. Now in solid earth geophysics, this may be different. Systems are not always noisy and can be very deterministic. So that changes also the way we apply data assimilation. The observations are indicated with the letter Y, and in atmospheric or oceanographic applications, this is typically temperature or sometimes velocity, salinity, pressure in the atmosphere. But in the reservoir, it will be the rate, production rate, as well as the bottom hole pressure of your well. Now, the observation is often related to the state, but this is not always a one-on-one relationship. So we use the operator H to relate the two, and then we realize that also in this observation, there is a certain level of noise. This can be instrument noise, can be ambient noise, it can have different sources. Now, mind you that, and I realize I'm talking to geophysicists in the audience, that for seismic inversion, people refer to this H as the model, whereas in data assimilation, the model is really the flow model, so it's this F. Now, I didn't realize this was animated. The Bayesian, the data assimilation can be cast in a Bayesian formulation, and we see then that basically the outcome, which is a PDF of the posterior estimate, is formed out of the prior estimate, which comes from your model, plus the likelihood of your observations. And that can be expressed here in Bayes' theorem, where the denominator is simply a normalization term. So when we present the data simulation problem like this, we realize that we actually don't really need an inversion from the data. We just need forward simulations to estimate these two distributions, and then by simply multiplying the two distributions, we will get our posterior. Now, please keep in mind the terms prior, likelihood, and posterior, because I will be using them in the rest of my presentation. And then when I use prior, think of that as typically your model estimate, whatever you know of the system before you start observing. Now, this is the equation I showed in the previous slide, where I mentioned that your observation can be C as an operator times the actual true state plus some noise. I put in this slide to stress that it's really a multiplication that is what gives us our solution. And the same is true when we do a parameter estimation, as is illustrated here. So we have the theta here, which could be your permeability or your porosity, and you're estimating your posterior parameters given your observations of the state. And that can be cast in a similar way as we did with the state estimation. Now, to make this presentation a little bit more lively, I created a poll, and Shelley, who is going to host this meeting, was supposed to put the poll into into Zoom, but that didn't happen. But we'll just try to see what happens if we use the chat function. Just to know how to tune the rest of my presentation to my audience, I wanted to test with you which profile fits you best. So what I suggest now is that the people in the room, I think everyone can use, or you can use the Q&A button. Oh, that's the questions, yeah. But can they also? They can also type, right? Renee?
Yes, everyone should be able to
Yeah.
use the chat function.
Okay. Yeah, there
yes.
I see. So I see a lot of A's.
People are entering here, so I can start writing this stuff down for you as well.
Ah, there is a B. Good. Yeah, and I see Mark is a D. Could have guessed that. Mostly A's. Oh, some geologists. That's good to see. Yeah, so I think if you agree with me that it's mostly A's, so mostly geophysicists in the room, some reservoir engineers, an occasional other, and an occasional geologist. So let's, actually, are you seeing this bar? With this in mind, I'll try to tune my presentation a little bit towards the geophysicist language, although in principle, geophysicists should be able to understand reservoir engineers and vice versa. But this is just useful for me on the rest of my presentation. So I'm going to show you a number of applications of research done in TU Delft, some of it in collaboration with Shell in, let's say, the last 20 years. And I'd like to start with an application which must relate to you as geophysicists, where we try to build a system that assimilates time-lapse seismic data. And now to assimilate time-lapse seismic data is quite tricky. So what Justina Pribic, who published this work, did is she started off with some synthetic data, where she imagined that any seismic image we would get, any 4D seismic image we would get, would actually give us an indication of saturation and would allow us to monitor the oil-water front. So that's shown here in the bottom 3 panels, where you see a front expanding. And in addition to these 3 seismic surveys, she assumes that we have all production rates at the producing well. Now, the Toy reservoir is quite a fantasy reservoir. So I apologize for the geologists in the room. The reservoir is square. It has 5 wells, an injector in the center, and producers in the corner. Hence this nice pattern of the front moving. And the permeability field is heterogeneous. So you see that there are some low perm streaks here that allow for an easy flow. Now, if we hold on. If we assimilate these data into our prior estimate of this permeability field, so we start the model off with a prior that is almost constant, then let's see what happens. And Justina used here a representer method, which is a variational method. And you see that actually the data assimilation is able to reconstruct this something that is quite similar to the original permeability field. But you also see that it really works a lot better if we use both the production data and the seismic. If we would just use the data, so the production data, so the rates in these 4 wells, we do get something like a low perm streaks here, but if we use that synthetic time-lapse seismic, we get a better image, and if we then reduce the noise in our seismic data, it becomes even better. Now, this work inspired some other research projects within a collaboration between TU Delft and Shell. And I also worked with Marcin Glegola. I noticed Ola Eiken is in the room as well. He's familiar with his work. And what we did here is we updated the both the parameters of our reservoir model and the geometry of our reservoir model, which is quite different from what usually is being done in history matching. What you see here, let me start with the left bottom panels. You see the initial estimates, so the priors indicated with the blue lines. You see many lines because we used an ensemble, so that's multiple estimates to describe this prior distribution. And then when assimilating the data, we were able to reconstruct the gravity signal, and you see a very tiny black line here which indicates the data, and you'll see that the estimated gravity signal is quite close to the data. And the same holds for the bottom hole pressure data that Marcin assimilated into the reservoir. And these signals, by the way, this is on the horizontal, is the x coordinate. So there's a section through the reservoir where we evaluate these parameters. So by doing data simulation, we improve the fit to the data. But then what's really interesting is to see whether you also improve the fit to the porosity and permeability fields, and that was also the case in this paper. For more details, I refer to this 2012 SPE paper. And as said before, the special thing about this system is that we were not only updating the parameters that I showed you before, we also updated the aquifer properties of the aquifer, giving the pressure support, as well as the configuration of the reservoir. So the top and bottom horizons of the reservoir may not have been perfectly picked, so we could adjust that with the data assimilation. Now, it would be fair to say that this has all been done on a synthetic experiment. We used a Bruges field for this. The Bruges field was initiated for a comparison project of different history matching methods, and it's publicly available and shared by TNO. But this is just to give you a feeling of how data simulation could work in practice and how some research projects have studied it. And I think what becomes clear from these examples is that you are always dealing with a misfit between model and data, even though in this case we worked with synthetic data. And we know that these differences come from two different sources. On one hand side, we have the model errors, the parameters that are uncertain, simplified physics, discretization. And on the other hand, we have data errors, measurement precision, accuracy, but also representativeness. So whatever we measure may not be representative for the model counterpart. And in our data simulation, we need to accommodate for both, but the challenge is really that we never really know the truth. So in the synthetic examples that I showed, yes, we do know the truth, but in a real example, we do not. So I'm now moving to the next part, which is about the different approaches. How am I doing with time? I'll probably be quick in this because a lot of this would be better understood if you go and read the papers, but I do want to give you an overview of these methods, and I'll highlight the method that we use in the COVID study so you know how this has been applied in our study. I mentioned to you before the essence of data simulation can be seen as estimating the posterior based on observations, the likelihood, and a model prior. And we're trying to maximize the likelihood to really see where is the peak of this PDF. And that can be seen as equivalent to minimize a cost function. And the geophysicists in the room that do seismic inversion will recognize the use of a cost function for this purpose. And as said before, we take into account the uncertainties both in the data and in the model. Now, the most common approaches in reservoir monitoring or in petroleum engineering are, first of all, the ensemble Kalman filter, which has a number of derivations. But then as we are estimating parameters, people have been adapting that method and finding out what works best in the case of optimizing parameters. And Dean Oliver introduced the random maximum likelihood method, which I will not discuss today. And Emmerich and Reynolds introduced the ensemble smoother multiple data simulation, which is the method that we also use in the COVID study. Then in other geoscience fields and occasionally also in assisted history matching, a very well-known method is the 4D VAR method. That's mostly used in meteorology, but now being replaced little by ensemble common filter like methods. And if you look at highly nonlinear systems, the use of the particle filter is also becoming more popular, and methods like particle flow and other sequential Monte Carlo methods. As said before, weather forecasting typically happens with 4D VAR. And 4D VAR is a variational method where we're minimizing a cost function. Now, the main ingredients here are the first term is about the difference between your forward simulation and your what we call the background. And that's really your initial condition. So you're trying to minimize the error in your initial condition. You're trying to stick to your initial estimate as much as possible within the error estimates of this initial condition. And the error covariance for that initial error is captured in the matrix B, which is also known as the background matrix. And then the other term, the other part of our cost function is governed by the misfit of the observations in your model. So we recognize the operator H on our model that translates the model to the model equivalent of our observations Y. And the RY matrix here is the error covariance matrix of our observations. So we're both minimizing this JO, this observational misfit, and the misfit of the initial conditions. And what we do is we run the model forward. When an observation comes in, we check how well it fits, and we go back and adjust the initial conditions to then improve our model estimate. And we do this iteratively to find the best solution. So this works very well for problems where the initial condition is what mostly the error in initial conditions is what determines mostly the trajectory of your model. It's a very elegant model. The disadvantage in a computational sense is that it requires the adjoint of the model. So what you see in weather centers is whenever a model is being adjusted, it's being improved, we need to update the adjoint of that model, and that requires a lot of coding. So over time, with increasing computer resources and perhaps less coders and programmers, we've seen a tendency to go more towards ensemble methods. Many of these ensemble methods are sequential, and this is the graph that I showed you in the beginning, just to remember you of the procedure where you run a model, the observation comes in, and you update the model. And you can see actually this model also as a set of models, a number of ensemble members or a number of particles. Now, in the ensemble Kalman filter, which is perhaps the most used method at the moment, we are also minimizing a cost function. I didn't put it on this slide, but it looks quite similar. But there we represent the observational errors by, again, a matrix R, but we also represent the model error by a matrix P. And this is very much as was done in the original Kalman filter. But rather than using Gaussian estimates, as was done in the Kalman filter, we base our model error covariance on a set of forward model runs. And so we update this model error, this model forecast error, every time we assimilate the data in a sequential manner, just as the previous slide. And that then you end up with an estimate for your state, which is the state in your previous time step, plus a multiplication of a lot of matrices, and you recognize the H in this model error covariance, times what we call the innovation, which is the misfit between your observation and the model operator times your model state. Now, what I mentioned before this, the PA is, and actually I think I made a mistake here because one of these has to be, I think this is a PA, is actually your analysis error covariance is a multiplication of a set of matrices times your forecast model error covariance. And this way you evolve both the estimate and its error estimate. It allows you to derive the mean of your analysis, which is then the final results of your data simulation, as well as error estimates from an ensemble of simulations. I always like to explain ensemble methods with the following picture, where you start at a certain time t and you run the model forward to time t is t plus 1. But you can already see that making assumptions of Gaussianity, as is often done in ensemble Kalman filters, may limit this representation. We are approximating the error covariances, and these methods do not always map the full probability density. Methods that should in principle be able to estimate these full probability density functions. But just to set you thinking about this problem, I have another poll, and the question will be, if you want to estimate this probability density function of your state in a reservoir model, and you want to really find how the PDF is propagating in time, how many of these black lines, how many of these ensemble members do you think you typically need? So we're going to do another poll. And those who think that with 10 ensemble members, you can actually model your probability density function can put in A. Those who think you need 100 can put in B. Those who think it's 1,000,000, and this graph has 1,000,000 dots really, can put in C. And those who think it's really more than that can put in D. So please type your answers. I see there is a unanimous choice for B. I also see that something happened with the order of my slides. So I'm for the explanation. Teresa. Thank you, Teresa. So I'm now going to show you and something happened to the order of my slides. So I'm going to quickly do this. This is the answer of the poll. Now, think about how many variables we have in a reservoir model, and then think about creating that PDF. So we would create a histogram, and typically to see the shape of that PDF, we need about 10 frequency bins. And then think about the variables in our model. Now, an average size reservoir model has a large number of grid points, and each grid point then has temperature, or not temperature, sorry, velocity, pressure, saturation, you mention it. Then we would actually need 10 to the million. We need to store 10 to the million numbers. So we would really need a massive ensemble. So I think Teresa, I can congratulate you on giving the correct answer. In practice, however, we know that a lot of model realizations are not independent. So that helps us. So in practice, we can actually run ensembles with 100 or even with 10 members. So the ones answering B and even no one answered A, but even with 10 members, I've seen successful data assimilation studies. Let me move back to where I wanted to be. Continuing now the presentation of the methods, I'm moving from this ensemble Kalman filter to a more of a smoother method where we use all the data at once. I don't want to go too much in detail as that would take a lot of time again, but again, we have a cost function to be minimized here, and we will now in this cost function assimilate all the observations of the entire period to be analyzed. And we introduce an iteration here. So this is now becoming an iterative optimization. And in that iteration, we're tempering the errors. So in the beginning, when we compare observations with model, we will have a large difference. And as we're updating sequentially, you will see that this error becomes smaller, and we're actually accommodating that by changing having this alpha factor here in the cost function. Now, the practical implementation is we sample initial ensemble members. So typically these are around 100 to a couple of thousand members. We generate a prior ensemble to actually predict the model counterpart, and I'm using here the letter gamma for that because that makes the notation here a little bit more elegant. And then we have an update very similar to the ensemble Kalman filter, but with the counter n+1, and for each iteration we compute the entire trajectory, so the entire time period, and we repeat this a number of iterations. Now, the last method I want to introduce, which is more perhaps more of a hobby for nonlinear lovers, than something that can be readily applied in reservoir engineering, is particle filters or particle smoothers, which is actually in a way the most intuitive or the most straightforward way to do data simulation. But the issue here is that if you want to use this method to propagate your PDF, you are no longer making the assumptions that we make in the ensemble Kalman filter, and hence to do this well, we would really need that 10 to the power 1 million ensemble members, which we typically don't do. So we need to use other tricks to accommodate for basically the lack of coverage in our solution space. Again, you will recognize the Bayesian formulation that I introduced in the beginning. And the idea now is that this this likelihood we're going to estimate by taking samples of our prior and comparing them with the observations. You will then actually generate, sorry, I'm mixing up here. The PX is the prior, and you're generating an ensemble of simulations that represent the prior distribution of your model. Now, you're also sampling this this model and comparing it to your observations, which gives you the weight W, where you you find an expression that puts a certain weight to your model prior. So you have an ensemble or a member, or you have a particle, and the closer it is to the observations, the higher this weight will be. Now, if we use this weight and we use this prior, we can actually express the nominator of this expression by a multiplication of the W times this sampled member. And that makes it a very intuitive methods, and it's easily explained with a graph, where you start off with a number of ensemble members, and I put a limited ensemble members here, or Peter Jan van Leeuwen did a limited ensemble members just for the reason of explaining the concept. You run these forward until your data come in, and then the closer these data are to your observation, the higher the weight. And the weight is expressed here with this probability density function, as well as with the size of these circles. So the higher, the closer this model run is to your observation, the larger the circle. Now you can imagine if you continue with those ensemble members, you will also have ensemble members or particles that are really way off from your next observation. And this is exactly the reason why, in order to do this well, you would need more than 1 billion ensemble members, because then you would have enough coverage to have sufficient members that end up here and that are still within going in the right direction for your actual true trajectory. So this is known as something called degeneracy. So the filter is degenerate, and then people working on a particle filter, particle flow, or particle smoother have different ways to actually make sure that your ensemble is not degenerating. Okay, so enough of the maths and of the methods. I would like now to move to the study on COVID-19. I'd like to emphasize that this is really teamwork. We worked with people from 8 different. Oh, sorry, Manika. Thanks for letting this know. I think you can watch the recording afterwards. So this is. A paper with 8 different countries participating, a highly international team, many people working in meteorology, but also a number of people working in petroleum engineering. And the case studies that we did with this team were in different countries. And this is showing you the it's still from July, I apologize for that, but the spread of the virus, the spread of the pandemic, and then the green stars are the countries where we did the study, and I think the star in the States is missing here, but the States is also included. So a number of European countries, which you see listed here, plus Quebec, USA, Brazil, and Argentina. Now, the COVID-19 epidemic and other epidemics can be modeled with the so-called SEIR model, and SEIR stands for susceptible, exposed, infected, and recovered. And you can see them here in different boxes. So we created different boxes for different age categories, and for each age category, you will see a different time for recovery, and a different time to move between those boxes. Also, the transmission between people is different for each age categories. Now, the Qs here are those in quarantine. The H's are those in hospitalized, where at some point we also made sure we captured the patients in the care homes, and the D is for the deaths. whereas the R's here are for the recovered, and we distinguish those with mild symptoms, RM, from those with severe symptoms, the RS. Now you can, I can tell you that each of these arrows represents an ordinary differential equation, and in these equations we have parameters or coefficients that we have a prior knowledge of, but that may not be entirely certain. So it's these parameters that we're estimating with this study. The parameters are listed here. A very important word, the initially exposed and initially infected, and this is a number we really do not know very well because not many tests were done in the beginning, and you really don't know how the people were exposed to each other. Then we have the well-known reproduction number. I think I hardly need to explain that to you. There's an incubation period as well as an infection time, recovering time, the time of hospitalization, and time it takes for people to from being severely sick to die. We have a fatality rate, which we make age dependent. There's hospitalization rate, which is also age dependent. And we also realized that not all of the people who fell ill were actually admitted to a hospital. Some of them stayed at home and died there. So a lot of different parameters here that go into the model. Now the observations, as the parameters are uncertain, also the observations are quite uncertain. Showing you here the numbers for England from different sources, and you can see quite a spread even in the number of deaths being recorded. And the same holds for the spread in France. And in France, the good thing is that there is a tracking of people dying in care homes, so that was something we could really use well. Now the approach that we then use is we chose a prior R reproduction number, and that's the reproduction number is illustrated here. It tells you how many people one person affects or can infect. So if the R is 1, then the number of people being infected will be quite stable. But if it's higher than R, you will see an increase of the pandemic. We chose initially exposed and infected. We looked at the demographics of each region, and then we assimilated the number of deaths and the number of hospitalized. For the Netherlands, we also assimilated the ICU beds. Some countries could work with the data of the infected, but actually those numbers were so uncertain that we didn't get any good results in some countries. And then we run an ensemble of 5,000 ensemble members or particles using this ensemble smoother multiple data simulation method. Now, realizing that quite a number of you may come from the US, I'd like to start with presenting some US results. And my colleagues from the University of Chapel Hill, North Carolina, studied 4 different states here, and they picked those states, well, they picked the state where they live, of course, but the other states were also based on their mobility characteristics. As in the initial stages of the pandemic, New York State experienced the largest reduction of mobility, 66% reduction. And also in California, there was a strong reduction in mobility. Should be said, though, that in New York, especially in New York City, people are using public transportation a lot, whereas in California, people typically use their cars, and that also has an impact on the spread of the virus. And then the other state was where there was not a very strong exposure, and also not many measures actually being followed. is Alabama. That's also studied. And we see a distinct difference in response. Now, let me try to explain what I'm showing you here. So there are 4 different panels, each giving you the reproduction factor for the specific state. We have a prior R that we allow a very large standard deviation. So in other words, we say that we really do not know this reproduction factor very well. So you can see that our prior ensemble, indicated with the light grayish blue lines, is very wide. And when we then assimilate the data, just as I showed with the gravity data and the bottom hole pressure data earlier on in my presentation, we see that actually this distribution narrows down a bit, and it is being lifted. So according to the data for Alabama, the initial reproduction factor was more around 3 than around the 1 that we assumed in our prior. And what is interesting to see here, and not surprising, is that the largest reproduction factor has been reached in New York. And we also see quite a strong decline here in New York, where it was so alarming that it it really dropped. People were really taking measures there. Another test was done where we assumed that we more or less knew this reproduction factor, and we assumed people were really adhering to the measures as imposed by the government. And then you see that in many countries we have a bit of a wavy response, which could, but this is a bit of speculation, could be related also to the fact that people were protesting against the measures and were going on the streets and simply no longer following the regulations. And you see that this effect is much less in New York, where people were really shocked and responded quite strongly to the initial strong onset of the pandemic. Now, with these estimates, we also have estimates of the hospitalized and the deaths, and this simulation only runs to July. We have not done, or we have not collectively done any updates. People have done this individually, but we did not update the graphs. But there you can see different behavior, and as a matter of fact, indeed in California, we did see a continued increase, whereas in New York, it was bending a little bit more. So you could interpret this as that the measures really, following the measures really helped to flatten the curve. Now, another thing I would like to present to you is that we looked at the predictability of our system. And this is work done by Peter Oetekamer in Quebec, where he really compared the 2-week forecast of our system with the actual observed deaths. And he compared a case in which he assimilated the deaths, the hospitalized, and the care homes, the cases, the number of infected, to a case with only death and hospitalized, and a case with only the death. And you see in all 3 cases a reasonable forecasting skill, except for the latter couple of weeks. And Peter's explanation is that possibly some changes in the way we deal with patients or the treatment may also have lowered the actual may mean that our model was no longer tuned well, and that we should have put in a time dependency in some of the parameters in order to account for that. Now, I would like to end up with the cases for the Netherlands. There, I simulated not only the number of hospitalized, but I also tried to work with the number of IC unit, intensive care unit beds, which were tracked with a little bit more accuracy than the number of hospitalized, especially in the beginning of the pandemic in the Netherlands. Only the people being admitted to hospital were being tracked and publicly available, and the number of COVID patients being released from hospital could not be inferred from data on the web. So that's why I started working with the intensive care beds. And then later on, I compared the two methods, and they gave actually quite similar responses. And just like my colleagues in the States, we here tried a large standard deviation in our prior for the reproduction factor, and you see that the resulting reproduction factor actually indicates that it must have been around 3.5 in the onset of the pandemic, and then it has been below when we really had lockdown, and now in the current period, well, this runs until July, but I've run it longer and it still remains around the 1. So there's not much exciting happening after this. But what was interesting to see is that the RIVM, the Dutch Health Institute, has been sharing a reproduction factor which looked more or less like the blue curve here. So that's the last experiment we did, where it was around 2 in the beginning and then gradually decreased. But when I tried an experiment with that as the initial guess, the data simulation was telling us that it was more likely that the R was actually higher than that and then decreased at about the same period as stated by the Health Institute. So all in all, this was a very interesting exercise. We had a lot of fun with an international group of scientists working on a domain that's really not ours. So our interpretation of the results should, we should put a cautionary note there. And actually, we published this also with an invitation to those working in medicine to help us out with a better interpretation of our results and perhaps also improve the system. So in brief, I see I'm already running over time. The data simulation provides an online automated estimation to monitor this reproduction factor. We have some large uncertainties in some of the data, but using data simulation, we could have a good forecast skill, which suggests that we can actually use this system to evaluate different scenarios, including the need and the impact of new intervention. So we are working on some new experiments where we would like to evaluate the forecasts for the period of the summer, but then we think we should really add a time dependency to some of the model parameters, which we've assumed to be constant. And what will be really tricky is to include the effect of travel, as well as, then we would really like to study the effect of different measures. And, once a vaccine is available, we should also see what is the effect of vaccination. So my takeaway messages to you is data simulation is a method that combines model and data. It's mathematically robust and it's efficient. It's automated in a way if you put in the right prior assumptions. It's being applied widely and successfully in oceanography and meteorology. It's becoming very popular in petroleum engineering, but you see it being picked up in other geosciences as well, like hydrology, geomechanics, but also different, things outside of the geosciences, financial world, in the biological sciences, as well as in this medical application. And the application of the COVID-19 learned us a lot of things about the behavior of systems like this, and about the use of ensemble smoother multiple data simulation for this purpose. And it may help us also to monitor, forecast, and prevent further spreading. And with this, I'd like to end my presentation. I really owe a sincere thank you to Mingji Wang, who's not here because she's on maternity leave, who invited me to this webinar, and to Shelley and Renee, who organized it, and Renee is hosting it today. And with that, I would gladly take your questions. Renee has already mentioned that you can use the Q&A function.
Yes, I also wanted to mention that the recording for this webinar will be made available on SEG Live. So we really appreciate all of you tuning in and listening, and your flexibility of starting a little bit late. So I really appreciate, thank you so much for presenting. It looks like we have a Q&A question here. I don't know if you're able to see it. Would you like me to read it for you?
It's my colleague Bill Russen.
Okay, great.
Thank you, Bill. That's a good question. And Bill asks, a value a reproduction factor of 2 suggests that each infected person infects 2 others. That's what I also showed in the cartoon. But over what period of time will this happen? Does the number of infected people double every week or every day? The answer here is that there is an incubation period during which there are no symptoms, but a person is already infected. And you should see that factor R really as something that's, that can be determined afterwards by looking at the number of people infected after the incubation time. And then statistically looking at how many people have been infected and how many people were infected before that incubation time. So statistically speaking, how many people have infected others? I hope that answered the question. Yeah, and then Dorit Kunich asks a very good question. Did you get a chance to discuss the discrepancy of your findings with the REVM, and what could this discrepancy relate to? I did not have a chance. I've been in email contact with the REVM, but they did not have time to work with me on this. I also hear from other colleagues in Delft working on COVID modeling that the REVM has not been very responsive, but I think this is a conscious choice because they really need to focus on their operational forecasts and their operational modeling. What could this discrepancy be related to? I think, so I've looked into the REVM method to compute this R, and it's much more statistical than that there's any physics behind it, as far as I can judge. And they're only working with the data, so it's data driven, and then the data that they have are only as good as they have them, and especially in the initial stages the data came with a very large uncertainty. So I think this is very much related to bad data, and by the way, that could also influence our results. So if we made wrong estimates on certain parameters, then it will also be reflected. So there's not really a right and a wrong, but it would be interesting to look a little bit more at what assumptions they made and what assumptions we made and how these compare. And but that would really require closer contact with the modeling people at the Health Institute. But thanks, Dorit, very good question. If no one is answering questions, perhaps a question to the audience. Is there anyone else in the audience who has been working on COVID, whether it's just for a hobby or because you have a medical background, or it remains very silent on the chat. So I guess this was all unexplored territory for the audience.
Well, one comment that I have, this is Renee, is that, you know, there's so many variables that go into this, and you touched on it at the end, is that you have, you know, the question of what if there's a vaccine now that we have all these different travel restrictions. There's so many variables, and how you try to tackle that just seems like quite a challenge. So perhaps that's part of the reason why maybe other people are interested in this but not have not tackled it themselves.
Yeah, that's a very right comment, Renee, and that's also why I think it would be really, you know, to make our next step, it would be almost essential to collaborate with the medical people, or the people modeling pandemics.
Well, again, I want to thank you so much for presenting, and really appreciated your talk. And this will be available on SEG Live. So thanks again, Femke, as well as Ming Wong and Shelley Oakley for making this possible. Thanks everyone for tuning in.